Hello friends and students, welcome to this video. Today I have selected a problem which involves Newton's law of motion and then pseudo force. Pseudo force is something which students are really confused. What is pseudo force? When to apply it? When not to apply it? So in this video, I'll take a problem and then I'll explain why we are applying pseudo force. Okay, so this is the problem. Let's solve it. The problem is find the mass m, this one, of the hanging block in the above figure, which will prevent the smaller block from slipping over the triangular block. All the surfaces are frictionless and the string and the pulley are light. This string and the pulley are light. Okay. So we'll draw the free body diagram of each component and we will see. And by applying the pseudo force, we will solve this problem. Okay, so let's understand the motion of what are the different motions in this system. This mass m has some weight, so there will be a gravitational force on this body. Because of this gravitational force, this will try to fall down, right? And since if all surfaces are frictionless, this triangular mass m dash will start moving towards right because it is attached through a string to this mass m, right? And then it will have some acceleration also because there is some force in this string in the form of tension which is pulling this towards down. So there will be some acceleration in this mass m also, and same acceleration will be there into this system also. Now since this wedge is moving towards right, this smaller mass m, since there is no friction between this smaller mass m and an m dash, if this system were in static position, this would have started falling down. But now, since this m dash is having an acceleration a towards right, and if this system, the smaller mass m, if it doesn't have to slip over capital M dash, what should happen? It means there should be a pseudo force we need to apply, right? Pseudo force is something which people are confused. So I will explain what is pseudo force. So if you stand on this, let us say you stand on this mass m dash, right? So if you stand here then with respect to this mass m dash, this smaller mass will not move, and that's what the problem is saying, right? Find the mass m of the hanging block in the above figure, which will prevent the smaller block from slipping over the triangular block, right? So, if you are going over this m dash, which is having acceleration a, right? In that case, this frame of reference m dash itself is having an acceleration a. So, in that case, you'll have to apply a pseudo force, which will be mass times acceleration, right? So that those are the motions of this system. So now let's try to draw the free body diagram of each individual component. Let's start with capital mass, right? So this is the capital mass mg, and then there is some tension in the string, let's say that is T, and let's say the downward acceleration of this mass is A, right? So now we can apply Newton's law of motion. Which law we should apply? We need to apply Newton's second law here, second law of motion, right? Because there is an acceleration. So what does Newton's second laws of motion says? It says that net force on a particle will be equal to mass time acceleration. So net force downward will be mg minus t, right? And that will be equal to mass times acceleration. So let's say that this is equation number one. Okay, now let's think of this bigger mass, right? Bigger mass of m dash. And then what will happen here? Let's first see this system. This system is looking like this. So there is some string attached to this which will have a tension T, right? And there is smaller mass m. Let's say that a smaller mass is applying some normal force n here, right? And then has its own mass, right? So its mass will have a gravitational force which will be equal to its weight, that will become m dash g, right? And one thing I missed was there was a angle here. This angle was theta. Okay. So now let's see. This angle will become theta, right? If this angle is theta, what will happen? Consider this triangle, this triangle. So this will become 90 minus theta. And if this is 90 minus theta, now consider this triangle. This will become theta, right? So I will just write it cleanly. This will become theta. Okay. Any other force acting on this? Weight m dash g downward, normal force n, tension T, right? Let's take the vertical motion. Apply Newton's second law in the vertical direction. Apply Newton's second law in the vertical direction. So, uh, if you apply vertical direction, but let's break the component of this n. So n is this way, right? So there will be two component of this. One will be in this horizontal direction, which will be how much? Theta is here, so this will be n sine theta, right? Just remember, wherever it makes angle, that component will be cos component. So this component will be n cos theta. Okay, n cos theta. Okay, now uh, so and then there will be some force by the surface or by the earth, right? Which will apply in the upward direction because this is wedge, right? So it is attached to the earth. It is resting on the earth. So earth will also apply some vertical force like this, which will be normal to this surface. Let us say this is n dash. So total how many force? N dash, which is the force, normal force by the earth on the wedge. N, which is the force by the smaller block, normal to the surface of on this wedge. Tension T towards the right, and mass due to mass m dash, its weight mg. Total four forces. So now let's see in the vertical direction. Vertical direction there is no acceleration, right? And but only horizontal direction, only acceleration is in the horizontal direction, which is a. So in vertical direction, the force will be balanced. So instead of this second law, I think that is also fine. Second law also you can apply. I can just mention that acceleration is 0, so it will be balanced. Here first law and second law is same because the acceleration is 0. So all forces in this vertical direction will be net. Net sum will be 0. So you can say n dash upward is equal to m dash g downward plus n cos theta, right? And uh, in horizontal direction, in horizontal direction, let us say the acceleration is towards right with a. So let's say net force towards right is T tension, right? What is the opposing force? Opposing force is n sine theta. This force n sine theta. So this net force is creating an acceleration which is a, right? So it will be equal to m dash a from Newton's second law. Let's say this is equation 2. Okay. Now let's see the smaller block, free body diagram of the smaller block. This is FBD, right? This is FBD. Oh, and this is also an FBD. FBD, right? Free body diagram. Okay. So let's see the FBD of the smaller block. The smaller block is resting on this inclined surface, right? Here also its weight mg will be downward, and this in this n normal force, this normal force will be again n, right? So whatever force this block was exerting on the wedge from Newton's third law, the same force in magnitude but opposite in direction will be applied on this block also, right? So they are the only two forces or any other force? Just see the system. I don't think any other force is there, right? Because the string T is not attached to this. It is attached to only um, wedge. Now we need to think of pseudo force, right? Because we are going to observe from this wedge, this which is itself is moving with an acceleration a. So now that this frame of reference itself has an acceleration a towards this direction, so you will have to apply a pseudo force in opposite direction, right? Which will be this way, this much. So it will be its mass times acceleration. Okay. Now let's see the angles. This is theta, right? And in the above diagram, we already saw this angle was theta. It means that it means this angle was theta. So if this angle was theta, then this angle will also be theta. So it's this component will be n cos theta, and this component will be n sin theta, right? Now let's see again. Apply the Newton's second law of motion in the vertical direction. direction, what will happen? There is no forces are balanced because you are on this frame of reference itself. So with respect to you, the system is at rest. So forces in the horizontal direction and vertical direction, they are both balancing each other. So vertical direction, what is happening? N cos theta equal to mg, right? Let's say this is third. Then n sin theta upward force, sorry, this rightward force n sin theta is equal to ma. This is 4. That's it. So how many unknowns we have? We have n and then n sin theta, n here also. So n and 2 one unknown, and then t is the second unknown, and then acceleration a is the third unknown, right? And we need to find the value of capital M. So capital M itself is an unknown here, 4 unknown, and then we have 1, 2, 3, 4 equations. Actually, this is not needed. This one is not needed because this is adding one equation, but this is also adding one unknown n dash. So it will not help. So you can ignore this one, right? So we'll just consider 1, 2, 3, 4. Okay. Now we just a matter of solving this. So divide 3 by 4. What you will get? 3 by 4, right? So we will get n cos theta by n sin theta equal to mg by ma. You can cut this n. So this means cot theta, right? Cos theta by sin theta cot theta equal to g by a, right? This means a equal to, do cross multiplication, g by cot theta, which is nothing but g tan theta. So you got the acceleration, value of acceleration. Okay. And if you put this value of acceleration into equation 4, what you will get? Put value of a in equation 4, right? You will get n sin theta m times g tan theta, right? So n will become mg tan theta is nothing but sin theta by cos theta, and this sin theta again came here. It means this sin theta you can cut. This will become mg by cos theta. Actually, the same thing you could have already get from equation 3. N will become mg by cos theta. So both will give the same result, right? I just took a longer path. Now we have got n, we have got a. What we need to find out now? T and m, right? So put this value into equation 1. Mg minus T equal to ma, right? So mg minus T equal to m. A is nothing but g tan theta. G tan theta, right? This is the one. So this will give T equal to mg minus mg tan theta. So you just take the common, mg common, it will become 1 minus tan theta. Okay, you got the value of n, you got the value of t. So let's put this value into in equation. Which equation? In equation 2. Okay, in equation t minus n sin theta equal to m dash a. T minus n sine theta equal to m dash a. And now let's put the value of all these. T is mg 1 minus tan theta minus n. What is the value of n we got? Mg by cos theta, right? Which m? Which m? Small m, right? Just be cautious. Mg by cos theta. And sine theta is already here. So just keep this sine theta here equal to m dash a. A is how much? G by g tan theta. G tan theta. Now let's solve. We need to find out the value of capital M, right? So we'll just keep this term here itself in the left side, tan theta, and everything will take this side. So this mg by cos theta into sin theta will become mg tan theta, and this is already here, m dash g tan theta. So this, if you take g common and tan theta also common, it will become small m plus m dash, right? Mg into 1 minus tan theta. So you can cut this g and g, and then let's put this tan theta this side. This will become 1 by 1 minus tan theta divided by tan theta equal to m plus m dash. This how much you can write? 1 by tan theta, which will become cot theta, minus 1, because tan theta by tan theta will become 1, equal to m plus m dash. So this gives m equal to m plus m dash. Let me write it clearly. M dash divided by cot theta minus 1. So this is the mass of the wedge. This should be the value of the mass of the wedge, so that in this system, this smaller mass m will not slip over the surface. This is what it will ask, right? Find the mass m of the block, hanging block. Sorry, not wedge, this hanging block. So this should be the mass of this hanging block, so that this smaller mass does not slip over this one. Okay, here one point worth noting is I applied a pseudo force here, right? I applied a pseudo force because I went, I just went over this wedge, right? So I am onto a frame of reference which has an acceleration a. There is another way you can solve this without applying pseudo force also. How? If you don't apply pseudo force, let's say you are still on the ground. So if you are on the ground, what you will see is this smaller block will be moving at an acceleration a, right? So in that case, let's solve this. Approach 2. Approach 2. Free body diagram will look like this. Without using pseudo force. Free body diagram will look like this. There will be a normal force, same, right? There will be mass, gravitational force, mg. That's it, right? So we just saw this. Why the angle, right? Let me re-verify. Yeah, this is why the angle. So here, what you will see is this will again n cos theta, n sin theta, mg. So what you will see is n cos theta is balancing here mg, n cos theta is balancing mg, and there is a net force n sin theta towards right, which is not being balanced by anything, right? Because you are looking from the ground. So this is the force which is creating an acceleration a in this smaller body, right? So because of this force, this will create an acceleration a. So you can write like n sine theta equal to ma. Now let's see this equation. N cos theta equal to mg and n sin theta equal to ma. Isn't it same? N cos theta equal to mg, n sin theta equal to ma. Like this. Both are same, right? So whichever way you apply, without applying a pseudo force or applying or with applying a pseudo force, answer will remain the same. Where here what it matters is from where you are looking. With you are looking from which frame of reference. If you are looking from a frame of reference which itself has an acceleration, like in the first case we just overrode on this wedge, so it has an acceleration, we will have to apply a pseudo force. In the second case, I am observing from the ground, right? I am observing from the ground. I am here on the ground. In this case, I will see that this mass is moving towards right with an acceleration a, right? So and then right, so in this case I'm not going to apply any pseudo force because I'm static. I am standing on a static frame of reference. So in this case there is no pseudo force, but the equation of motion will look like this net force will be equal to mass time acceleration. So whatever way you solve, if you apply the concept correctly, the answer will remain the same. Okay, so solve this, you will get same result. Okay, so that's it for now.